Welcome back to the Deep Dive, where we sift through the latest research and most compelling ideas, extracting the absolute most important insights for you.
Mm-hmm.
Our mission today is to cut through the noise and get you genuinely well-informed on a topic that's truly buzzing in the world of large language models.
Yeah, there's always something new.
Right. And this one feels pretty fundamental. It's about how we teach them to generalize, to truly understand and perform beyond the specific examples they've seen during training.
That core challenge.
Exactly. That feeling when you're trying to master a new skill and you wish there was a shortcut to understanding the fundamental why behind it, rather than just rote memorization.
Absolutely, more than just mimicry.
Well, today we're diving into some fascinating new research that might just offer exactly that kind of shortcut for LLMs.
Indeed. Today, we're exploring a paper titled On the Generalization of SFT, a reinforcement learning perspective with reward rectification. It offers a fresh, maybe even revelatory perspective on supervised fine-tuning, or SFT, a foundational and widely used method for training large language models.
SFT, yeah, pretty much everyone uses it at some point.
Exactly. And what's particularly exciting is that it proposes a remarkably simple, yet profoundly effective improvement.
Simple is good.
Simple is often best, right?
Yeah.
This deep dive will help us understand the subtle, often overlooked mechanics of how these powerful models actually learn.
Okay.
And crucially, how a small, elegant tweak can lead to significant and, frankly, surprising gains in generalization, which is, as you said, often the holy grail in AI development.
Okay, let's truly unpack this then. We've always faced this huge, persistent challenge with LLMs, getting them to generalize robustly across diverse tasks, especially in complex reasoning.
It's a constant struggle.
And we're looking at a new approach here called dynamic fine-tuning, or DFT.
DFT, yes.
That promises to make a big splash by fundamentally addressing this generalization issue.
That's the claim.
So our goal for you, our listener, is to walk away not just understanding that standard SFT struggles, but why it struggles.
The mechanics behind the failure.
Right. And then how DFT elegantly fixes it with what's described as an almost unbelievable one-line code change.
Yeah, the simplicity is quite striking.
And the incredible, often counterintuitive impact this has had in challenging areas like mathematical reasoning, even outperforming methods far more complex than SFT.
Some really eye-opening results.
Get ready for some serious aha moments that might just redefine what we thought was possible with straightforward fine-tuning. So before we get to the groundbreaking stuff, let's set the stage, because understanding the landscape is key to appreciating this new insight, isn't it?
Absolutely. Context is everything.
What exactly are supervised fine-tuning, SFT, and reinforcement learning, RL, in the context of LLMs? And why has there historically been this constant tension, this almost philosophical tug of war between them?
Right. It's a fundamental trade-off that has defined much of the recent progress and indeed the challenges in LLM development. So, supervised fine-tuning, SFT. It's incredibly popular, primarily because of its simplicity and efficiency.
Easy to get started with.
Exactly. Imagine you have a powerful, general-purpose, pre-trained, large language model. It's read the entire internet and knows a lot, but it's not specialized.
Right, it's general purpose.
Now, you want it to perform a very specific task, say, generating persuasive marketing copy, or maybe accurately answering complex legal queries or solving specific math problems.
So tailoring it.
Precisely. With SFT, you provide it with a carefully curated data set of expert demonstrations.
Examples of good answers.
Perfect examples, essentially. Input A leads to desired output B. You're showing the model meticulously exactly what you want it to do.
Like teaching by example.
It's akin to a student observing a master artisan trying to replicate every brushstroke or every intricate movement.
Okay.
This approach is often compared to behavioral cloning in robotics, where a robot learns a skill by simply mimicking a human operator's actions.
Just copy what I do.
Exactly. SFT works by minimizing the difference between the model's generated output and the expert's output. It allows the model to quickly acquire those specific behaviors.
Makes sense.
It's straightforward to implement, computationally less demanding than other methods, and can rapidly get a model to a good baseline performance on tasks where you have plenty of correct examples.
And that sounds like a perfectly sensible approach on paper, right? If you just show a highly capable model what to do, it should learn.
Seems logical.
But this paper highlights a significant, almost inherent drawback to this mimicry.
Precisely. While SFT is excellent at imitation and efficiently getting a model to perform specific demonstrated tasks, its primary weakness, as you hinted, is generalization.
Ah, the G word.
The big one. The research literature is, well, it's full of discussions on how SFT tends to memorize the training data rather than truly understand the underlying principles, rules, or logic that govern the tasks.
So it learns the answers, not the method.
That's a great way to put it. Think of a student who can flawlessly recite entire passages from a textbook or perfectly solve every problem they've been shown, but then struggles profoundly when faced with a novel problem that requires applying those concepts in a slightly different way.
Yeah, we've all seen that.
This leads to overfitting. The model performs brilliantly on the specific examples it's seen, the exact phrases, the exact problem structures, but then its performance can drop significantly, sometimes drastically when faced with novel, slightly different scenarios or variations that weren't in its training set.
It's brittle.
Very brittle. It's an inability to adapt, to infer the deeper transferable logic. This is a widely acknowledged limitation, with some research explicitly stating that SFT memorizes while RL generalizes.
So that's where reinforcement learning comes in. If SFT is prone to memorization, RL steps up as the champion of generalization.
That's the typical narrative, yes.
How does RL manage to cultivate that deeper understanding, though?
Well, RL offers a fundamentally different paradigm for learning. Instead of just showing expert demonstrations and asking the model to mimic them exactly, RL provides the model with reward signals or verification signals for its actions.
So feedback, not just examples.
Exactly. It doesn't tell the model what to do, but how good its attempt was. This allows the model to explore diverse strategies and pathways, to try things out, and then to learn from its successes and failures over many iterations.
Trial and error, but guided.
Guided trial and error, precisely. It's like a student who isn't just given the answers, but is allowed to experiment, make mistakes, and then receives objective feedback on the quality of their attempt.
Okay.
Through this process, incentivized by rewards, the model can ultimately discover more robust and generalizable policies.
Policies meaning strategies.
Yes, strategies for generating good outputs. It learns not just what the good actions are, like SFT, but why certain actions lead to better outcome.
The underlying logic.
Exactly. This enables it to apply those principles effectively to new, unseen, or even highly challenging situations.
That sounds like a much more sophisticated and, frankly, a more human-like way to learn.
Yeah.
It clearly aims for that deeper, transferable understanding we're always after in AI.
It does.
But if it's so superior for generalization, it must come with its own set of significant challenges, right? Nothing's ever a silver bullet.
Absolutely. You've hit on the core trade-off. While RL offers superior generalization capabilities, it comes with significant practical hurdles that often make it difficult to implement at scale.
Like what?
Firstly, RL approaches are notoriously computationally expensive, they often requiring vast resources in terms of computing power, time, and data generation.
It takes forever.
It can, yeah. Training an RL agent involves many iterations of generating responses, evaluating them, and updating the model. It's a cycle. Secondly, they are highly sensitive to hyperparameter tuning. Even small changes to settings like learning rates, exploration parameters, or the design of the reward function itself can drastically impact performance.
Deadly to get it right.
Very fiddly. This makes them notoriously difficult to set up correctly and reliably, often requiring extensive expertise and experimentation.
Right.
And crucially, they depend heavily on the availability of reliable reward signals. Designing an accurate, consistent, and unbiased reward function for complex tasks, well, it's hard.
Especially for things like creativity or nuanced answers.
Exactly. Especially in real-world applications where correctness can be nuanced or subjective, it isn't always easy or even feasible. So while RL can generalize better, it's often a much heavier lift.
More demanding.
More expertise, more resources, and considerably more time to get right compared to the relative straightforwardness of SFT.
So to summarize, we have SFT easy, fast, efficient for demonstrated tasks, but limited in generalization due to its tendency to memorize. And on the other side, RL superior for generalization, capable of deeper understanding, but complex, computationally intensive, and tricky to set up.
Yeah.
Given this clear and frustrating trade-off, it's no surprise that researchers have spent a lot of effort trying to bridge this gap with hybrid methods. What do those typically look like in practice?
Hybrid approaches are indeed very common and currently represent a dominant line of research in making LLMs more aligned and useful.
Combining the best of both worlds, hopefully.
That's the goal. Many involve an initial SFT pre-training phase. This early SFT step is often used to get the model to a stable, expert-like starting point.
Laying a foundation.
Exactly, allowing it to rapidly acquire basic behaviors, output formats, and foundational knowledge from a large corpus of human-generated demonstrations. This provides a strong foundation.
Okay.
Following this, an RL-based refinement stage is often applied. A well-known example is the Instruct GPT approach.
Right, that made waves.
It did. It famously involved training a separate reward model on human preferences, meaning humans ranked different LLM outputs for quality.
Ah, so getting that tricky reward signal from humans.
Yes. Then, reinforcement learning, specifically proximal policy optimization, or PPO, was used to fine-tune the LLM based on the feedback from this learned reward model.
PPO.
PPO, for those unfamiliar, is a powerful and popular algorithm in RL that acts like a highly sophisticated trial and error coach, helping the model refine its actions in small, stable steps, always guided by a reward signal.
Got it.
Another prominent example is direct preference optimization, or DPO.
DPO, yeah, heard a lot about that too.
It simplifies this by bypassing the explicit reward model. Instead, DPO directly optimizes the LLM's policy on preference data itself.
So no separate reward model.
Correct. You provide pairs of responses, one preferred over the other, and the model learns to generate the preferred one. It effectively integrates imitation and reinforcement signals into a single, elegant loss function. However, what's fascinating and crucial here is that these methods typically augment the training pipeline. They add layers or stages around SFT or use different types of data like preference pairs or negative samples.
They build on top of SFT.
You're right. They don't fundamentally change or improve SFT itself. They build upon its output or work around its limitations by adding more complex machinery.
This raises an important question then. Can we fundamentally improve SFT itself? Can we make it generalize better? Especially for those incredibly common real-world scenarios where we only have positive expert demonstrations and no easy way to get negative samples, preference pairs, or complex reward signals.
The standard SFT setup.
Exactly. Can we make SFT itself a more robust and generalizable learning paradigm without adding all the computational and data complexity of RL or external reward models?
That's the million-dollar question.
And this is precisely where our deep dive truly begins, into how this new paper addresses that exact persistent challenge. Here's where it gets really interesting and where this paper offers a truly foundational insight.
Yeah, this is the core contribution.
It dives deep into the mathematical core of SFT, beyond just its practical application. It sounds intimidating, but the insight they uncover is incredibly clear.
It really is.
And helps us understand not just that SFT struggles with generalization, but why it struggles, pinpointing the exact mechanical flaw. It's like discovering the precise faulty cog in an otherwise powerful machine.
That's a good analogy. The researchers performed a rigorous mathematical analysis, something that previous work had sort of hinted at, made general connections about.
But hadn't nailed down.
Exactly. Hadn't fully established with such precision and clarity. They rigorously demonstrated that the standard SFT gradient update, which is the mechanism by which the model adjusts its internal parameters during training.
How it learned.
Right, how it learns, can actually be interpreted as a special case of a policy gradient method.
Policy gradient, like in RL.
The very same type of gradient used in reinforcement learning to update an agent's behavior. It's a crucial and often overlooked link between what we commonly perceive as supervised learning and reinforcement learning.
So SFT is secretly doing a kind of RL under the hood, even when we explicitly frame it as supervised learning.
Kind of, yeah.
That's quite a revelation, suggesting the lines between these paradigms might be far blurrier than we typically imagine.
It appears so. It's operating with an implicit reward structure. However, as they reveal through their meticulous analysis, this implicit reward isn't just basic or unoptimized. It's fundamentally problematic in a couple of critical ways. It's not just an absence of a good reward, but the active presence of a bad one that creates instability.
Problematic how? What specific characteristics did they discover about this hidden internal reward that SFT is unknowingly using?
They discovered that this implicit reward is both extremely sparse and, critically, inversely proportional to the policy's assigned probability of expert actions.
Okay, two things. Sparse and inversely proportional.
Right. And these two characteristics, when combined, create a highly unstable and inefficient learning environment for the LLM.
Okay, let's unpack extremely sparse in this context. What does that mean for the model's learning signal?
Imagine you're searching for a treasure in a vast desert, And only a tiny speck of that desert actually contains the reward if you land exactly on it.
So, very rare feedback.
Extremely rare. In the context of SFT, the reward is essentially only given when the model exactly reproduces the expert's entire response character for character, token for token.
Match only.
Perfect match only. If the model generates a sequence that is even slightly off, if it produces an output that is logically correct but expressed differently than the expert demonstration, or if it makes a single error along the way,
Nothing.
it receives zero implicit reward. Most of the time, for every other possible generated sequence that isn't an exact, perfect match to the expert, the implicit reward is zero. This makes learning incredibly inefficient and difficult because the model gets very little positive signal to guide its exploration. It leads to a lot of wasted computation and slow progress.
Like learning blindfolded most of the time?
Pretty much. It's like learning to play a complex piece of music, but only being told, good job, if you play the entire piece flawlessly from start to finish, and nothing if you make a single wrong note.
That sounds frustrating. And then the second characteristic, inversely proportional to the policy's assigned probability of expert actions.
Yes.
That's quite a mouthful, but it sounds like the real core of the pathology here. Could you simplify that for us?
It is indeed the core of the problem, leading to what they call unbounded variance.
Unbounded variance. Sounds bad.
It is. Think of it this way. If the model is very unconfident about an expert action, meaning it assigns a very low probability to generating that particular correct token or sequence.
So it thinks it's unlikely to be right.
Right. But then the implicit reward it receives for actually generating that correct expert action becomes enormously high.
Wait, so it gets a huge reward for something it thought was wrong.
Or very unlikely, yes. Conversely, if the model is already confident and assigns a high probability to an expert action, the reward it gets for reproducing that action is very small.
Okay.
The mathematical term for this is an important sampling weight of one boy, where POF is the probability the model assigns to the expert action.
Got it.
When POF is very small, meaning the model thinks the expert action is very unlikely, then one poi becomes very large, disproportionately amplifying the reward.
So if the model gets something right by accident, or if it's really struggling with a particular rare part of the expert demonstration, and it happens to generate the correct token,
Frame.
the reward signal it gets is disproportionately magnified precisely because it was so unlikely.
Exactly.
That sounds incredibly counterproductive and unstable for learning.
It is. This phenomenon leads to what they call unbounded variance in the reward estimates. Imagine trying to learn to drive a car where the steering wheel sensitivity changes wildly and unpredictably depending on how slow you're going or how unsure you are about making a turn.
Okay, yeah.
One moment it's completely unresponsive, the next it oversteers dramatically with the slightest touch.
Nightmare.
It creates a pathological optimization landscape where the learning signals are erratic, unstable, and extremely noisy. This makes it incredibly hard for the model to find a consistent, stable path to improvement.
So it's getting confusing signals.
It's not just a lack of good information, but misleading information that can send the model wildly off course.
That sounds like an absolute nightmare for any learning system. So this combination of extreme sparsity, very little feedback, and this volatile inverse probability weighting amplified unstable feedback is the root cause of SFT's poor generalization. It's not just an inefficiency, it's an act of sabotage of its learning process.
That's the groundbreaking conclusion presented in the paper. Because of this large variance and the extreme sparsity, the optimization process in standard SFT tends to overfit to rare exact match demonstrations.
Focusing on the weird hard parts.
Exactly. The model tries too hard to precisely replicate those tricky, low-probability expert actions that, when achieved, yield an outsized, unstable reward. This intense focus on exact reproduction, especially of infrequent or difficult examples, undermines its ability to learn broader, more robust patterns that would allow it to generalize beyond the training data.
So it sacrifices general understanding for specific memorization.
Precisely. This insight is truly foundational because it doesn't just restate that SFT generalizes poorly, which, let's be honest, we kind of knew.
Yeah, that wasn't news.
But it rigorously explains why at a fundamental mathematical level. It shows that SFT isn't just lacking a reward, it's operating with a bad one that actively sabotages its generalization capabilities.
This precision is what makes the paper's contribution so impactful. The mathematical equivalence between the SFT gradient and an offline policy gradient explicitly identifying this inverse probability weighting term, 1, as the key differentiator, the specific pinpointed flaw.
Yes, the smoking gun, so to speak.
It suggests that perhaps the lines between imitation and reinforcement learning are even blurrier than we thought, and that we've been fundamentally misinterpreting SFT's true problematic nature all along.
It certainly seems that way.
Does this mean countless hours were spent trying to patch symptoms when the core problem was a faulty engine all along? So we've identified the problem. SFT's implicit, wild, and unstable reward system, driven by extreme sparsity and that problematic inverse probability weighting.
The faulty cog.
That's a clear diagnosis of the faulty cog.
Yeah.
Now for the solution, and this is where the paper proposes something surprisingly elegant and, as you noted, incredibly simple to implement. It's called dynamic fine-tuning, or DFT.
DFT. Building directly on that rigorous mathematical analysis, DFT offers a principled and remarkably elegant solution to the root cause of SFT's generalization problem.
Okay.
The core idea is to rectify the reward by dynamically reweighting the SFT objective.
Rectify the reward, like fixing it.
Essentially, yes. It neutralizes that problematic one-L-verse weighting term we just discussed, transforming the erratic reward landscape into something much more stable and conducive to learning.
And how does it achieve this reward rectification in practice? What's the precise mechanism for this reweighting without adding all the complexity of a full RL pipeline?
It's surprisingly direct. For each token in the expert demonstration, the method simply rescales the standard SFT objectives with the probability of this token.
So it uses the model's own probability.
Exactly. Mathematically, it means multiplying the SFT gradient by a corrective inverse ratio, given by the model's own policy probability for that specific token, pipex.
Okay, multiplying by pay.
Right. It's a direct surgical counteraction to the one-pay term that was causing all the trouble.
So, if I understand correctly, it's essentially saying, hey, model, if you're really confident about generating this token correctly, Bessie is high, we're not going to let that previous mechanism give it an outsized reward that makes you overfit. And if you're less confident, pace is low, we're not going to let the unlikely success amplify the reward in a way that creates instability.
Precisely.
It directly neutralizes that problematic inverse weighting, making the effective reward signal for each token much more uniform and stable.
That's a very accurate way to put it, and it beautifully captures the essence of DFT by applying a stop gradient operator.
Stop gradient? What's that?
Think of it like a one-way street for information or a valve that only allows water to flow in one direction. Gradients, which are the learning signals, don't flow back through this scaling term.
Okay.
This is crucial because it ensures the scaling term acts purely as a reweighting mechanism. It effectively tells the model how important or how much attention this piece of information should get, but the model isn't trying to optimize that weighting factor itself.
It just uses it as a scale.
Exactly. This single-line code change fundamentally transforms the gradient estimator. It moves it from being an unstable, biased, and probability-dependent mechanism, which we found in standard SFT,
The pathological one.
right, to a stable, uniformly weighted update procedure. The implicit reward for every correct token in the expert trajectory effectively becomes a uniform one, rather than a wildly fluctuating value based on the model's current confidence.
A single line of code, really. That sounds almost too good to be true for such a fundamental and widely recognized problem in LLM training.
I know, right?
It's like finding the master switch for a deeply complex system. That level of elegant simplicity for such a profound impact is truly remarkable.
It truly is remarkable in its simplicity and effectiveness. The practical implementation involves applying this important sampling at the token level, which is a common and numerically stable practice in these kinds of models.
So it works token by token.
Yes. The result is that the reward in this corrected SFT, which we're calling DFT, effectively becomes uniform for all expert trajectory tokens.
A flat reward.
A flat, consistent reward. This uniform reward is critical because it avoids overconcentration on specific low-probability reference tokens.
Which caused the overfitting before.
Exactly. That overconcentration was the source of so much instability and overfitting in standard SFT. Instead, DFT provides more stable updates and, crucially, improved generalization.
And the kicker.
And it does all this without introducing any additional sampling, without needing a separate reward model, and without the iterative environment interaction, which were the big computational hurdles and complexities of traditional RL methods.
So, in essence, DFT achieves the benefits of a more stable, consistent reward signal Similar to what you'd ideally want from reinforcement learning, but without any of the added baggage.
None of the usual RL overhead.
No computational expense, no intricate pipeline design.
Nope, that's a huge practical advantage. Indeed, it's a testament to how deep theoretical insight, when applied surgically, can lead to incredibly practical and efficient solutions. What's also fascinating is how this approach contrasts with other established ideas. For example, focal loss in computer vision.
Focal loss, right? I remember that.
Focal loss, if you recall, downweights well-classified samples to help the model focus on underrepresented or difficult to classify examples, aiming to improve performance on rare classes.
Okay, focus on the hard stuff.
Right. DFT, conversely, effectively downweights poorly classified samples that generate those unstable high-variance gradients.
So it downweights the noisy signals.
Exactly. To improve generalization, it's almost a diametrically opposite philosophy.
That's wild.
It suggests a fundamental shift in focus for LLM fine-tuning, where the challenge of overfitting, that is, the model becoming too good at the specific training data but failing on new examples, has become a more pressing and prevalent problem than underfitting.
We're making models that memorize too well.
It seems so in many cases. We're seeing models that are often too good at memorizing the exact training data, and DFT is teaching them to generalize by making the learning signal more consistent and less susceptible to the allure of those noisy high-variance rewards.
So if standard SFT was unknowingly operating with a problematic internal reward system that led to unstable learning and an unfortunate tendency to overfit,
Which it was.
then DFT essentially gives it a much healthier, more consistent, and ultimately more truthful reward system.
That's the idea.
It's like moving from a flickering, unreliable light source in a dark room to a steady, clear beacon, leading to much better, more robust learning and generalization without the usual heavy lifting.
A really nice way to put it.
Now for the part that really sells it, the experimental results. We've talked about the problem, and we've introduced DFT as the elegant fix.
The theory sounds good.
But as we often say in AI, the proof is in the performance. Let's dig into the experimental results to see just how dramatically this one-line code change impacted LLM capabilities.
Right. Does it actually work?
Especially in those notoriously difficult areas that truly test a model's understanding.
And they focused on mathematical reasoning, which is, as you noted, an excellent test bed for generalization.
Why math specifically?
Because it inherently requires true understanding, logical step-by-step thinking, and the application of principles, not just simple pattern matching or regurgitation.
Can't just fake it till you make it.
Exactly. You can't just parrot back answers. You need to solve novel problems. The data set used in the paper, Numinomath Code T, is quite extensive,
How extensive?
comprising around 860,000 diverse mathematical problems paired with their corresponding chain of thought solutions.
COTI, chain of thought, so it shows its work.
Right. Code T, for those unfamiliar, is a technique where the model is prompted to think out loud by generating intermediate reasoning steps before arriving at the final answer. This helps evaluate not just the correctness, but the logical process.
Makes sense for math.
And the dataset problems were sourced from various challenging domains, including Chinese high school math and international Olympiads, ensuring a high bar.
So tough problems. What about the models?
To ensure the results weren't specific to one model architecture or scale, the researchers used a diverse range of state-of-the-art base models for fine-tuning.
Good practice.
These included various sizes of Qwen 2.5 math, like the 1.5b and 7b parameter versions, Lame 3.23b, Lame 3.18b, and DeepSeek Math 7b.
A good mix of recent models.
Definitely. They then evaluated the performance on established, widely recognized, and difficult benchmarks like Math 500, Minerva Math, Olympiad Bench, AME 2024, and AMC 2023.
Okay. The usual suspects for hard math benchmarks.
Yeah, hard stuff. Yeah.
And the comparison between DFT and standard SFT on these challenging benchmarks is pretty stark, demonstrating a clear and compelling win for the new approach.
Absolutely. The results are indeed compelling and paint a very clear picture. DFT consistently and significantly outperforms standard SFT across all evaluated LLMs and most benchmarks.
Every single one.
Pretty much, yeah. For instance, let's look at the Qwen 2.5 Math 1.5b model, one of the smaller but still highly capable models tested. DFT achieved an impressive average gain of plus 15.66 points over the base model's performance before fine-tuning.
15 points. That's huge in these benchmarks.
It really is. And to put that in perspective, this improvement from DFT is over 5.9 times larger than the modest plus 2.09-point improvement observed from standard SFT on the same model.
Wow, so SFT barely moved the needle, DFT sent it soaring.
Relatively speaking, yes, and we see similar substantial patterns across other model families and slices.
Like the LLM.
Yep, the LLM 3.23b model saw a plus 3.46-point gain with DFT, which was approximately 1.4 times SFT's gain. The LLM 3.18b achieved plus 10-point zoo from DFT, surpassing SFT's plus 5.33 by 1.88 times.
Still significantly better.
DeepSeek Math 7b saw a plus 15.51-point improvement via DFT, which was 1.58 times larger than SFT's plus 7.18. And Quen 2.5 Math 7b reached a plus 15.90-point gain, nearly 3.8 times higher than SFT's plus 2.37.
Consistent gains across the board. These aren't minor differences or incremental tweaks, are they?
Not at all. They represent substantial shifts in a model's capability for mathematical reasoning.
That's a remarkable across-the-board improvement. But the really critical point, the one that truly validates the generalization argument, is how it performs on the most challenging benchmarks.
Right, the Olympiad-level stuff.
Those tests where simple memorization completely falls apart. This is where true understanding is separated from superficial pattern matching. Did SFT actually fail on these, and did DFT still shine?
That's precisely where DFT truly shines and emphatically demonstrates its robust generalization capabilities. On benchmarks like Olympiad Bench, AM 2024, and AMC 2023, these are the really tough ones.
The ones that make humans sweat.
Exactly.
Yeah.
Often requiring advanced multi-step reasoning, creativity, and deep conceptual understanding, standard SFT often yielded minimal or even negative impact.
Negative. It made the model worse.
Yes, you heard that right. In some cases, the model's performance degraded after SFT compared to the base model's pre-fine-tuning scores.
That's the classic overfitting problem.
Textbook overfitting. The model has learned the training data too specifically and lost its broader reasoning abilities. For example, on Olympiad Bench, SFT actually caused the Quen 2.5 Math 1.5b model's accuracy to drop from 15.88% to 12.63%.
Ouch. It literally learned to perform worse on hard problems.
Correct. In stark contrast, DFT boosted that exact same model to an impressive 27.08%.
Huge difference.
Which is a plus 11.2-point improvement over the base model. On AME 2024, SFT reduced accuracy for the larger Quen 2.5 Math 7b by 4.21 points, from 6.68% to a dismal 2.48%.
Terrible.
DFT, however, improved it to 8.56%, achieving a plus 1.88-point gain over the base model, which is significant given the extreme difficulty of Hayden problems.
Even a small gain there is impressive.
It really is. A similar trend was observed on AMC 2023, where SFT reduced the performance of Quen 2.5 Math 1.5b from 19.38% to 18.75%, while DFT raised it significantly to 38.13%.
Whoa, nearly double the base performance.
An astounding plus 18.75-point gain over the base model. These results unequivocally underscore that DFT not only scales more effectively across models, but also exhibits far greater resilience and genuine reasoning capability on difficult tasks where traditional SFT struggles significantly, often actively making the model worse.
Wow. SFT actually made models perform worse in some of the hardest scenarios, and DFT made them dramatically, almost unbelievably better.
It's quite stark.
That truly underscores the generalization issue, doesn't it?
Yeah.
It shows SFT isn't just inefficient or limited, it can be actively detrimental for truly complex abstract tasks.
Seems that way, yes.
Beyond just accuracy, how does DFT impact the actual learning process itself? Does it learn more efficiently or faster?
Yes, absolutely. The paper provides compelling evidence that DFT leads to better learning efficiency and faster convergence.
Faster learning is always good.
Always. For those following along, if you look at the accuracy progression graphs in Figure 1 of the paper, you can see very clear differences in learning dynamics between DFT and standard SFT on the Quen 2.5 Math 1.5b across all mathematical reasoning benchmarks.
What do they show?
DFT consistently achieves peak performance much faster, often reaching its optimal accuracy within the first 120 training steps.
That's quick.
Very quick in the grand scheme of training these models. Crucially, it also shows better early-stage performance, frequently outperforming SFT's best final accuracy within just the first 10 to 20 steps of training.
So it gets good almost immediately.
Relatively speaking, yes. This indicates significantly higher sample efficiency, meaning it needs fewer updates and less data exposure to reach optimal results.
Less data, faster result.
Exactly. This accelerated convergence suggests that DFT's dynamic reweighting mechanism leads to more informative and stable gradient updates from the very beginning. It guides the model toward high-quality quality solutions much earlier in training.
Avoiding wasted effort.
Right. It effectively helps the model avoid the meandering optimization paths, the noisy plateaus, or the sudden drops in performance often encountered in standard SFT, enabling a more efficient acquisition of complex mathematical reasoning patterns.
They also compared DFT to a concurrent method called importance-weighted SFT, or IWSFT, which sounds like it's also trying to address some of these weighting issues you've discussed.
Right. Similar goal.
How did that stack up against DFT? Was it a close race?
That's a pertinent question, as IWSFT is indeed another effort to improve SFT through weighting mechanisms. Generally, DFT outperformed IWSFT in most settings.
DFT still came out on top.
Yes, particularly in terms of overall robustness and consistency. For instance, DFT achieved higher average accuracy on models like Lemma 3.23b, Llama 3.18b, DeepSeek Math 7b, and Qwen 2.5 Math 1.5b compared to IWSFT, with gains ranging from plus 1.3 to plus 4.15 points.
Okay, so noticeably better.
And what's particularly noteworthy is that IWSFT sometimes showed signs of limited robustness. It even performed worse than standard SFT on certain benchmarks for some Lemma models.
Worse than SFT. That's not good.
No. For example, for LMA 3.23b, IW-SFT scored lower on Math 500 and AMC 23 than standard SFT. This suggests IW-SFT might struggle to generalize effectively and could actually degrade performance on harder benchmarks.
So maybe less reliable than DFT.
It seems so. And crucially, from an efficiency standpoint, IW-SFT requires a separate reference model to compute its importance weights.
Ah, extra complexity.
Exactly. It adds computational overhead and complexity to the pipeline. DFT, on the other hand, derives its weighting directly from the model's own token probabilities, making it more efficient and self-contained.
No extra model needed.
Nope, no additional external components. So DFT is not only more effective, but also simpler.
That's a key distinction. Not only is DFT more effective and robust, but it's also simpler and more efficient to implement than other advanced SFT variations that are trying to tackle similar problems.
Big practical advantages.
But then they took it a step further into an exploratory experiment in the offline reinforcement learning setting,
Yeah, this is really interesting.
where explicit reward signals are available. This is really pushing the boundaries of where a fine-tuning method might typically operate, essentially putting it head-to-head with dedicated RL techniques.
It was a surprising and powerful validation of DFT's underlying strength and the fundamental correctness of its reward rectification idea.
How did it do against actual RL methods?
In this offline RL setting, where explicit numerical reward signals are indeed available, DFT achieved the best overall performance with the Qwen 2.5 Math 1.5b model.
Better than RL methods.
Yes, it surpassed both established offline RL methods like direct preference optimization, DPO, and reward feedback training, RFT, which are specifically designed for this type of data and often complex to implement.
Beat DPO and RFT.
Wow. And even more impressively, it outperformed strong online RL algorithms such as proximal policy optimization, PPO, and generalized reinforcement policy optimization.
Beat PPO too.
Yes, which are generally considered state-of-the-art for learning from interaction with an environment. DFT achieved an average score of 35.43, exceeding the best offline method RFT by a significant plus 11.46 points, and outperforming the strongest online RL algorithm GRPO by plus 3.43 points.
That's incredible.
The gains were particularly notable on challenging benchmarks like AMC 23 and Minerva Math, further underscoring its robustness.
That's incredibly significant. It means this simple yet effective fine-tuning strategy, born from fixing an SFT flaw, can actually beat methods that are designed specifically for RL.
It appears so in this setup.
Methods which are usually far more complex, resource-intensive, and require intricate pipelines. It really speaks volumes about the fundamental correctness and power of the reward rectification idea.
Precisely. It strongly suggests that DFT can serve as a more efficient, scalable, and powerful alternative to traditional RL pipelines, especially in domains where preference supervision or simple correct-incorrect reward signals are available.
But full RL is too much hassle.
Exactly. Where full-blown reward modeling or online response sampling is expensive, impractical, or simply too complex. It offers a strong, stable learning signal without the iterative reward modeling, the extensive hyperparameter tuning, or the environment interaction typically required by complex RL.
So it kind of bridges the gap in a new way.
It seems to. This exploratory experiment solidifies the notion that DFT's principled approach to reward rectification has broad applicability, potentially extending far beyond just the initial SFT setting, where only positive demonstrations are available.
So we've seen the incredible results across various models and benchmarks, even outperforming dedicated RL methods. That's the what?
The performance gains are clear.
But why does DFT lead to such fundamentally different outcomes at a mechanistic level? They actually looked at how DFT changes the token probability distribution within the model.
Yeah, looking inside the black box a bit.
And this is truly insightful into how the model is learning differently. It's like looking at the model's internal thought process.
This analysis is crucial, as it helps us understand the fundamental difference in how models trained by DFT think, or rather, how they allocate their confidence in generating tokens compared to standard SFT and other RL methods.
So how does SFT allocate confidence?
Standard SFT, driven by its problematic implicit reward system, tends to uniformly increase token probabilities across the board.
Boost everything.
Pretty much. It essentially tries to fit the training data more tightly by boosting all token probabilities, mainly focusing on the lower and lowest probability tokens to bring them up to confidence.
Trying to make everything highly likely.
Right. It's like a diligent but uncritical student trying to perfectly memorize every single word of a textbook, regardless of its importance or whether it's a core concept or just a filler word.
Memorize every comma.
Exactly. The goal is simply to reproduce the expert demonstration exactly, with high confidence across the board, even for inconsequential elements.
And DFT, given its reward rectification and the uniform, stable reward signal, does something quite different then.
Radically different, yeah.
It seems to foster a more discerning learning strategy.
Exactly. DFT exhibits a profound polarizing effect on these token probabilities.
Polarizing, like pushing things to extremes.
Kind of. Instead of uniformly boosting everything, it significantly boosts the probabilities of a subset of tokens, the ones that are semantically important and contribute to the core understanding of the task.
The important stuff.
Right, while actively suppressing the probabilities of others, pushing them towards lower confidence.
So it learns what not to be confident about, too.
Precisely. This leads to a more pronounced bimodal distribution, with more tokens occupying both the highest and lowest probability bins. It creates a sharper contrast in what the model considers important versus unimportant.
Interesting. How does that compare to RL?
Interestingly, other RL methods also show a similar trend, though usually milder in comparison to DFT's pronounced effect. This suggests this polarization is a hallmark of robust generalization.
That's a key distinction and a huge aha moment right there. So what kind of tokens are being suppressed or pushed into those lower probability bins by DFT? What exactly is the model learning to deprioritize?
They found that these are generally conjunctive words or punctuations, such as the, lead, wet.
Wait, really? Like the and commas?
Yeah. In other words, the model learns to assign significantly lower confidence to grammatical functions, common connective words, or punctuation marks that, while necessary for a coherent sentence, don't carry the primary semantic content or the critical logical steps needed for, say, mathematical reasoning.
So it figures out those aren't the key parts for solving the math problem.
It implicitly recognizes them as less critical for the core task.
That's an incredible insight. It means DFT is essentially developing a more intelligent filter, learning to deprioritize these more functional tokens. And in doing so, allowing the model to focus its precious learning capacity and attention on the substantive, semantically important concepts and logical steps within the mathematical reasoning.
Right. Focus on what matters.
It's like a human student learning to skim over the filler words in a lesson and focus intensely on the core ideas, the formulas, the problem-solving steps, rather than obsessing over every single preposition or article.
That's a great analogy.
That's a highly intelligent and efficient form of learning, rather than just brute force memorization.
Exactly. This suggests a powerful principle. For robust learning, models should not attempt to fit all tokens with uniform confidence.
Interesting.
It's a very human-like approach to learning and information processing. We filter, we prioritize, we focus on what's critical for understanding.
Right.
By strategically down-weighting the probability of these less critical tokens, DFT likely contributes significantly to its improved generalization. The model isn't expending precious learning capacity trying to perfectly reproduce every single inconsequential word.
Saving its brain power for the hard stuff.
Instead, it's building a more conceptual and principle-based understanding, which is paramount for tasks like mathematical reasoning, where the how and why are more important than exact phrasing.
And to round out the investigation into DFT's practicality, they also checked how sensitive it was to common training hyperparameters like learning rate and batch size.
The usual suspects.
which can often make or break a new method's real-world usability. Was DFT a delicate flower or robust enough for practitioners?
Good news there. The ablation study confirmed its robustness. DFT consistently outperformed SFT across all tested learning rates, from very small to relatively large.
So it's not just lucky hyperparameter tuning.
Doesn't seem to be, no. It confirms that the significant performance gap isn't just due to SFT having suboptimal settings. Both methods do show some sensitivity to learning rate, with intermediate values generally performing best.
Usual Goldilocks zone.
Exactly. Too low, and it learns slowly. Too high, and it becomes unstable. However, both DFT and SFT were remarkably stable across a wide range of different batch sizes, ranging from 32 to 256.
Batch size didn't matter much.
Not a dominant factor in this setup, suggesting practitioners don't have to spend excessive time and resources on hyperparameter tuning for DFT to be effective.
That's great news for adoption.
Absolutely. This robustness further adds to DFT's practical appeal, making it easier for developers to integrate into their existing SFT pipelines. #outro.
So what does this all mean for you, the curious learner, and for the future of large language models?
Bringing it all together.
We started this deep dive with the fundamental, persistent challenge of getting LLMs to truly generalize, moving beyond simple memorization to genuine understanding and adaptability.
The core problem.
We then zoomed in on supervised fine-tuning, a popular but deeply flawed method, to uncover its hidden Achilles heel, an implicit, wildly unstable reward system within its own gradient that causes debilitating overfitting by disproportionately valuing unlikely successes.
That hidden problematic engine.
And then we saw how dynamic fine-tuning, or DFT, with its elegant one-line code change to dynamically reweight the SFT loss, precisely rectifies that unstable learning process.
The simple fix.
It transforms a noisy pathological landscape into a stable, highly effective one. The experimental results are truly impressive,
Yeah, quite striking.
demonstrating not just significant performance gains over standard SFT, especially on difficult mathematical reasoning tasks where SFT often fails dramatically,
Right.
but also surprising strength and efficiency in competitive offline reinforcement learning scenarios, even outperforming methods specifically designed for RL.
That was a really key finding.
It's a fantastic example of how a deep theoretical understanding, truly peering into the mathematical foundations of how these models learn, can lead to an incredibly practical, high-impact solution.
Basic research paying off.
It's not about throwing more data or more layers at the problem. It's about fundamentally rethinking how these models learn from expert demonstrations, identifying a core, subtle flaw, and fixing it with surgical precision.
It's a testament to the power of understanding the fundamentals.
What's profoundly fascinating here is the implication that we might need to shift our entire paradigm when thinking about LLM learning.
A different way to think about training.
Perhaps the goal isn't to meticulously fit every single piece of information, every single token, with equal confidence,
Which SFT tries to do.
but rather to discern what's truly essential, what carries the core semantic weight and logical significance, and what can be strategically deprioritized.
Learn what matters, ignore the rest.
This selective attention to information, this polarizing effect on token probabilities, seems to be a key unlock for much broader and more robust generalization, mirroring how human brains often learn effectively by filtering out noise.
A more human-like learning strategy, maybe.
This work was primarily focused on mathematical reasoning tasks and evaluated on models up to 7 billion parameters, as well as being text-only.
Important caveats.
But the core insight about token probabilities and reward rectification, and this idea of polarizing what the model focuses on, feels incredibly general and universally applicable.
The principle seems broader, yeah.
So for you, what might this mean for future LLM development beyond math tasks or even beyond text itself?
Good question.
Could this shift in thinking about what to learn from demonstrations, moving from blanket memorization to discerning semantic importance, be a critical key to unlocking even broader and more robust AI generalization?
Maybe.
Perhaps even in areas like complex code generation, nuanced common sense reasoning, or even multimodal models that combine vision and language. That's something truly worth mulling over and perhaps even inspiring future research for you out there.
Food for thought, definitely.
That's all for this deep dive. Until next time, keep learning and stay curious.